All right, 5-4 is solving by taking roots. So still solving these quadratics, just a different way, right? Giving you all the tools for your toolbox to solve these. All right, so our objectives today, we're going to still solve quadratic equations by taking roots. We're going to simplify radicals, including those with negative radicands. That's going to be new, a little bit different. And we're going to solve some real-world applications involving quadratic equations. Okay, so equations in the form of x squared minus c equals 0, in which c, okay, c is a perfect square, can be solved using the factoring method from the previous lesson or by taking roots. Okay, to solve by taking roots. This is what we're doing today. We're going to isolate the squared expression. Okay, so that's the first thing, isolate the squared expression, and then take the square root of each side of the equation. Doesn't sound too terrible, right? Like we can do this. Okay. However, let's look at the solve by factoring that we did in lesson 5.3 so we can compare the two. Okay, so if we're going to use this solve by factoring, our C term is here, right? Negative 81 is our C term, but we don't have a B term. Since there's not one, the B is actually 0. So what are the factors of negative 81 that would give me 0? Well, 81 is a prime or is a perfect square, so we would have negative 9 times a positive 9 would give me 81, but negative 9 plus 9 would also give me 0. Okay, so with that being said, we could set this up as x minus 9 is one factor, x plus 9 is the other factor, set equal to 0. Then we use that zero product property and set both of these equal to 0, right? X minus 9 would equal 0, or x plus 9 equals 0. So if we figure out those, we could get x is positive 9. On this one, we would subtract 9 to get x is equal to negative 9 as our solutions. Okay, so on B here, we're going to solve it by taking roots. And remember, the taking roots says we're going to isolate the squared expression. So we have x squared minus 81 equals 0 is our equation. We're going to isolate the squared, so we're going to add 81 to both sides. We get x squared equals 81. The next step is to take the square root, okay, square root of each side of the equation. So the square root of x squared is x. The square root of 81 is 9. Now, the thing here is, like we usually, this is kind of what we say, but don't forget that the square root of x squared is equal to the absolute value of x. Okay, is what we typically do. And we say, oh, okay, well, it's 9. However, the number x inside the absolute value, this could be a 9, because that equals 9, or it could be negative 9, would also equal 9. So here, we can't say the absolute value, or the square root of 81 is 9. We actually have to describe it as a positive or a negative 9, because it could be either one. Okay, this is some older information we need to bring back and not forget that we're looking at when we do the square root of x squared or any number, we usually, like we've always just taken the absolute value of that number. Now that we're in higher level math, we need to give it both, the positive and the negative sign. Okay, that's what this square root property here, right? The square root property states that if x squared equals k, and k is greater than 0, then x plus or minus the square root of k. Okay, so radicals should always be simplified. There are no perfect power factors in the radicand and no radicals in the denominator to simplify those. And that's missing right here. This should say x equals. I knew that was, I didn't read that right. So if x squared equals k and k is greater than 0, then x equals plus or minus the square root of k. So plus or minus, always, always, always. All right, so let's look here at simplifying radicals and rationalizing the denominator. Okay, because it says radicals should always be simplified. Always. That means there's no perfect power factors, okay, in the radicand, and no radicals. So no perfect power factors and no radicals in the denominator. So let's look here at simplifying radicals. The first thing we're going to do is we're going to write the radicand as the product of its prime factors. I love prime factorization. I love a factor. Like some people like factor trees. I like prime factorization since I found it. It's really easy to do. We're going to take this number, 400, like whatever's under the radicand, and we're going to divide it by a prime number. So, and I start down here because it's like we're going to do division, and it's going to build up like a tall birthday cake with lots and lots of layers. Okay. So 450 I could divide by 5. Remember, I have to divide by prime numbers. Actually, let's make it a little easier even, although 45 is, or divided by 5 is not hard. You could divide by 2, 3, 5, okay, any prime number, 7, any prime numbers you want. So let's divide it by 2. 450 divided by 2 is 225. Okay, 225 I can divide by 5. So 5 goes into 22 4 times. I have a 2 left over for 25. And so 25 divided by 5 is 5. 45 I can divide by 5 again. That's 9. 9 I can divide by 3 again. That's 3. Suddenly I'm done because I have a prime number on the top. Once I have a prime number at the top, I am finished with my prime factorization. So the product of my prime numbers are just these prime numbers. So the square root of 450 is equal to the square root of 2 times 5 times 5 times 3 times 3. Okay, so I write it as the product of its prime factors. Then I can simplify, okay, which is pretty awesome because we want the square root. Okay, we know that the square root of 16 is 4. The reason that is because the square root of 4 times 4, right? 16 we break into its product of its prime, well, this is not prime numbers, but the products of two other factors, and 4 times 4, because 4 times 4 equals 16. We need 2 of the same thing. So I have 2 5s here, so I can pull a 5 out from underneath my square root. And I have 2 3s, so I can pull a 3 out, because the square root of 5 times 5 is 5. The other way that might be helpful to write it is, what's the square root of 2 times 5 squared times 3 squared? And it's a square root, so I have a 5. The square root of a 5 squared is 5. The square root of 3 squared is 3. Okay, and then I keep the 2 under my square root because I'm able to pull those out. So right now, it's equal to 5 times 3 times the square root of 2, which we're going to finish up, and we're going to combine these terms. 5 times 3 is 15 times the square root of 2. That is the simplified radical there. Hopefully that wasn't terribly confusing. But okay, let's try B. Maybe it'll get less confusing with B if I have confused you. Okay, so we're going to write each number because this is the same thing as saying the square root of 50 divided by the square root of 3. Okay? Well, 3 is already a prime number, so we can't do anything else with it. Okay, but 50 we can do some work on. So I'm going to come over here, do 50 divided by 5, that's 10. 10 divided by 5 is 2. 2 is prime, so I'm finished. Right? Those are my 3 prime factors. So this is equal to the square root of 2 times 5 times 5 divided by the square root of 3. And you can always look at this differently too, like 5 times 5 is 25, 25 times 2 is 50. Instead of when I did it, I did 2 times 5 is 10, right? The opposite, you could check it here, 10 times 5 is 50. There's lots of ways to check that, so that's okay. All right, so we would factor, because we have 2 5s, we can pull that out, right? The square root of 5 times 5 is 5. So this is going to be 5 times the square root of 2 over the square root of 3. All right, but here's the thing. It said that there can be no radicals in the denominator. We currently have a radical in the denominator. So that's when we need to look here at the rationalizing the denominator. We need to simplify the numerator and the denominator, which we did. Multiply both the numerator and the denominator by the radical that makes the radicand in the denominator a perfect power. Say what? So let's see. Multiply both the numerator and the denominator by the radical that makes the radicand. Okay, in the denominator a perfect power. All that means is we're going to multiply by the number in the denominator. Okay, so I'm going to multiply this by the square root of 3 over the square root of 3, because that would equal, in the denominator, we would have the square root of 3 times, we would have 2 3's under there. Well, now that I have 2 3's, I can bring those 3's out, right? And just have a 3 in the denominator. So, and I guess I should go ahead and do the part up here. So I have 5 times the square root of 2 times 3. The 3 and the 2 can both go under the same radical, which is going to equal 5 times the square root of what? Good, 6 over, what's my denominator? Since I have the square root of 3 times 3. Excellent, my denominator is just 3. Now I no longer have a radical in my denominator, and I have simplified this. So the square root of 50 thirds is equivalent to 5 times the square root of 6 divided by 3. You will use this a ton in trigonometry, okay? Simplifying those radicals and rationalizing the denominator. A bunch of stuff in trigonometry. Okay, so taking roots allows us to solve some quadratics, okay? We can solve some quadratics that can't be solved by factoring integers, okay? Because sometimes that factoring integers gets complicated. This same procedure can be applied to equations containing a binomial that is squared, okay? So it's helpful if we just have a binomial and some quadratics we can use it on as well. So solving quadratic equations by taking roots. Our steps here are to isolate. We walked through them, but we're going to look at them. We're going to isolate the squared expression on one side of the equation. Apply that square root property, so take the square root of both sides, and then simplify the radical. Again, we did it in example 1, but we're going to have it there to remind you so that we can do it some more. So, example 3, let's solve these. Both of them are binomials, okay? So it makes it a little easier. Okay, we want to isolate the squared term. So that means we're going to add 100 here. We have 3x squared equals 100. Okay, have we isolated the term yet, the x squared term? No, we have not. We need to divide by 3. That's going to be the thing, right? Isolate means we're truly going to get the x squared term by itself. Okay, so now we have x squared equals 100 divided by 3. All right, the next step is to use the square root principle or property. So we're going to take the square root of both sides, which means x is going to equal plus or minus, throw that in there, the square root of 100 thirds. And this is why we just talked about simplifying the radical and rationalizing the denominator. Because when we're taking square roots, we have to have those skills. That's why people generally don't like taking roots very much. Like this is probably their least favorite way to solve quadratics because they are unfamiliar and uncomfortable with this part right here. Okay, so again, let's do the prime factors of 100. So if I take 100, we can't divide it by 10 because 10 is not prime. Okay, although we are taking the square root of it. So let me back that train up. So this is going to be equal to plus or minus the square root of 100 divided by the square root of 3. Well, I said we could write the prime factors, but we don't need to because 100 is perfect already. Like it's a perfect square, so we know it's 10. All right, so our x is going to equal plus or minus 10 divided by the square root of 3. All right, now we have this problem that we have a radical in the denominator, so we need to rationalize it. What are we going to multiply by to get rid of this denominator? Perfect. We're going to multiply by the square root of 3 over the square root of 3. So x is going to equal plus or minus 10 times the square root of 3 divided by 3. Because the square root of 3 times the square root of 3 just equals 3. Perfect. Let's look at the x squared over, or b. So we have x squared minus 8. We want to isolate our squared term, so we're going to add 8 to both sides. X squared equals 8. What's the next step? Good. Take the square root. So x is going to equal plus or minus the square root of 8. Okay, 8 is not a perfect square, so we can do its prime factors. Right? 8 divided by 2 is 4. 4 divided by 2 is 2. I have a prime number on the numerator on the top there, so I know that I'm done. So x is equal to plus or minus the square root of 2 times 2 times 2. Well, 2 of these are needed for a square root to pull out. So x is equal to plus or minus 2 times the square root of 2. That is our solution there. We have simplified that or solved it, however you want to look at it. Got that done. Okay, example 4 says solve 4 times the quantity y minus 2 squared plus 6 equals 114. And state the solutions as both simplified radical expressions and as a solution set containing decimal approximations to the nearest hundredth. Okay, so we're going to do these two different ways. So let's start out with our equation here. All right, we've got 4 times y minus 2 squared plus 6 equals 114. All right, is it in standard form? No, it's not. So what do we need to do? Well, we could put it in standard form. Okay. We're also dealing with taking the square root, right? We're solving by taking roots. We have a square term here, so we can isolate. Let's isolate this term and start there. So the first thing we would do is subtract 6 from both. So they're going to have 4 times the quantity y minus 2 squared equals 108. Okay, what would I do next? Perfect, I need to divide by 4 because it's with my squared term here. So I'm going to have the quantity y minus 2 squared equals, what's 108 divided by 4? Excellent, 27. Hopefully you got that down anyway. What's the next step? Good, we're going to apply that square root property. So we're going to take the square root of both sides. That will give us y minus 2 equals plus or minus the square root of 27. Perfect. 27 is not a perfect square, so we got to do some work over there. Okay, so we're going to find its prime factors. I know I can divide it by 3. 3 divided by, or 27, pardon me, divided by 3 is 9. I can divide by 3, and I get 3. So 27 is equal to 3 times 3 times 3. So y minus 2 is equal to plus or minus the square root of, and you could write it as 3 squared times 3, if that helps you, because then you're like, oh, well, the square root of 3 squared is 3, and then 1 3 is going to stay under the square root, if that helps. You can write it any way you want. Okay, now we need to isolate the variable to actually solve. So we're going to add 2 to both sides. So we would have y equals, now the thing about this too is we always put the number in front. We could say plus or minus 3 times the square root of 3 plus 2, but we're going to write this 2 first. It's going to be 2 plus or minus 3 times the square root of 3. It's generally less confusing to put the whole number in front. All right, so this answer is the simplified radical expression. Now you need to write it as a simplified decimal approximation to the nearest hundredth. Okay, so that just means you need your calculator and you need to put in 3 times the square root of 3 and press equal. When you do that in your calculator, you're going to get y equals 2 plus or minus 5.20, which is great. But now we need to actually put the answers there. Okay, because that means that y is equal to 2 plus 5.20 and y is equal to 2 minus 5.20 because of the plus or minus. So we have to do both of those to get that decimal approximation. So y equals 2 plus 5.20 is 7.20 as 1. And for the next one, y equals 2 minus 5.20 means y equals negative 3.20. And you're probably thinking like, Mrs. Talbert, we don't really need the 0 right on here, except that we do because it said to the nearest hundredth. We're following directions. Like we could take the 0 off and just write 7.2, but it asks us to write it to the nearest hundredth. So no, we cannot. All right, I'm going to erase. And we're going to start talking about an imaginary unit. Today is the day you get to talk about imaginary math. I know, you thought you already did imaginary math, but you haven't. All right, so if we look at this example, we're solving x squared plus 1 equals 0 by taking roots. It's going to produce the following results. Okay, so let's check it out. So x squared plus 1 equals 0. We subtract 1 from both sides, and we get x squared equals negative 1. Then we take the square root of that, and we get x equals plus or minus the square root of -1. But we can't take the square root of a negative number. This is impossible, right? It's not a real number, so it is designated as imaginary. We just say that the square root of -1 equals an imaginary number. This is huge. Okay, the square root of -1 equals I, an imaginary number, because we can't take the square root of a negative number. So that's what it is. An imaginary unit, or I, is the square root of -1. So we have I equals the square root of -1, and I squared equals -1. So if anytime you see I squared, you can replace it with -1. Anytime you see plus or minus the square root of -1, it's going to be written, or you can rewrite it as plus or minus I. So all we're doing is taking the square root of -1 and replacing it with a lowercase I because it's imaginary. That's what an imaginary number is. So if we break this down, the square roots of negative numbers are always expressed in terms of I. So if we have the square root of -9, we just say, well, okay, that's the square root of 9 times the square root of -1. The square root of 9 is 3. The square root of -1 is I, which is why we can write it as 3I. Okay. Here with the square root of -12, we could say, all right, well, that's just the square root of 1 times 4 times 3. Well, then we can say, well, 4 was not prime, so we could break it down a little further to say it's equal to the square root of 1 times 2 times 2 times 3. I have 2 2's, so I can bring those out. My negative square root of -1, I can replace as an I. So I have I times 2 times the square root of 3. And so when I simplify it, I always write the number first, and the I comes after. So it's 2I times the square root of 3. Lots of stuff going on there. The other thing, I, 3I, and 2I times the square root of 3 are called pure imaginary numbers. We'll get into those a little bit more, pure imaginary numbers and some of the differentiations later, but that's just for you to know at this point. Okay, so back to our square root property. A little bit more about this. So if x squared equals k, and we're adding to it, k is greater than 0, then x has two real solutions. X is going to be plus or minus the square root of k. If k is equal to 0, then x has one real solution. So this is the key here, right? One real solution, or two real solutions. One real solution, and that's x is equal to 0. If k is less than 0, then x has two complex solutions. And that just means it can be imaginary. Okay, it can be imaginary. It can have a radical in it, whatever. Well, it said it's imaginary. Complex would be an imaginary number. Okay, so lots of great stuff there. So you know we're going to use this in example 6, right? That's how this works. So let's do it. We're still solving. We're going to solve by using our taking roots, okay, because we have binomials. So we're going to isolate our squared term, subtract 45. So then we have m squared equals -45. We're going to take the square root of both sides. So now I have m equals plus or minus the square root of -45. It's that -45, the negative, that's throwing us. So remember, this is equivalent to the square root of -1 times 45. Okay, 45 is not a perfectly prime number, so we can do those prime factorizations, or you could say, hey, that's the same thing as the square root of -1 times 9 times 5, and 9 is a perfect square. Okay, so we could say m equals the -1 is an I, The square root of 9 is 3, and 5 doesn't have a square root, so we're going to leave it underneath the square root symbol. So m is equal to, I should put the plus or minus, I forgot that there. So m is equal to plus or minus 3i times the square root of 5. Imaginary numbers are not too difficult. It really is just replacing the square root of -1 with an I and saying it's imaginary. Okay, so let's look at B. Okay, let's look at B here. It's very similar to the one we just did as well. We've got our squared term here, the quantity W plus 3 squared. So let's isolate that to get us started. Okay, so let's subtract 10 from both sides. Then we get 2 times the quantity W plus 3 squared equals 2 minus 10 is -8. Let's divide by 2 on both sides. So then we have W plus 3, that quantity squared, equals -4. We take the square root, right, of our term, and we have W plus 3 equals plus or minus the square root of -4. Which is kind of nice because that actually is a square, right? There is a square root to that. So we could say, all right, well, this is, we have a square root. This is equivalent. Let's do that. So we have W plus 3 is equal to plus or minus, I'm going to break this down, the square root of 1 times 4. Okay, and maybe you're like, Mrs. Talbert, this is ridiculous. We got this. I just want to make sure. The negative square root of -1, right, can be replaced with I. The square root of 4 is a 2. So now I have W plus 3 equals plus or minus I times 2. Which, remember, I'm going to change that to be plus or minus 2i. We always just write it like when we write variables. We put the number first and then the letter. Okay? We need to isolate the W. That's our variable. The I is not a variable though, right? It's a known value. So we're going to subtract 3 from both sides. So W is going to equal -3 plus or minus 2i. So you're going to get some really wonky looking answers, and that's okay. You're learning that that's what math gets really weird looking, right? If you didn't learn that with matrices last chapter, you're learning it now, that math gets really weird looking. All right, that's it for this lesson, so we'll see you tomorrow.